Okay, angular momentum. We're going to have a couple. I want you to guess, actually probably the last one I'm going to teach you. If this was linear momentum, what were our rotational equivalents of mass and velocity? What was mass? Good. So you should already know one of these formulas. We're going to end up with I and omega at the end, but we're starting with just a point mass for a moment. Imagining just one point mass, typically rotating about something, but it doesn't even actually have to be rotating about something. Just has to have a distance away and moving by at a certain velocity. So this bottom one is sort of our first angular momentum formula for a point mass. And this is a cross product, so we would still use right-hand rule stuff. Okay, so M, mass of that object times R cross V. So like I said, cross V really. Got to be perpendicular. So the particle does not actually have to be rotating in a circle to have angular momentum. It just has to be moving relative to a reference point. So it can be moving in a straight line. It can have linear momentum, and we can still actually describe its angular momentum as well. So 278. Would you like to go 2 for 2, Zach?
We could. There we go.
Yes. Did you just see me looking at her? Did I have a tell? I had a tell. Wow.
Wait, did I really get it?
Yeah.
Yes. Oh my God.
Okay. And let's actually just look at our formula while we do this. So 278, checkpoint number 4, in part A of the figure. So part A, you've got particles going around a circle. Part B, you do not. In part A of the figure, particles 1 and 2 move around point O in opposite directions in circles with radii 2 meters and 4 meters. In part B, particles 3 and 4 travel along straight lines in the same direction with their closest distance to point O being 2 and 4. Particle 5 moves directly away from O. All 5 particles have the same mass and the same constant speed. A, rank them according to the magnitude of their angular momentum. So, we're ranking them all based on their mass, which was the same, their velocity, which was the same, and the radius. So which one's going to have the greatest angular momentum? Erica.
I guess the one with radius 4.
Which would be which one? Or ones? Particle 1 and three. All right, let's look at 3 for a second. So there's particle 3 moving along. Wouldn't you say its radius is much bigger? By radius, I mean, vector from our rotation point from O to it. Isn't that bigger than 4? Because it said the distances were 2 and 4 at their closest points. So shouldn't 1 and 3 tie? But why is it they tie? Why isn't 3 bigger? It's got a bigger R. It's got the same mass. It's got the same mass, got the same velocity. But the R is clearly bigger for object number 3.
I guess it couldn't be rotating if it were going this way, if that
going in a straight line.
Well, we can technically calculate the angular momentum even if it's not actually going in a circle about something. That's what they're saying. Okay, but here's what we're missing, this part right here. Does it matter really what the actual R is? No. What matters is the R that is perpendicular to the velocity. So if velocity is that way, I really actually only care about the 4. Okay, so 1 and 3 tie, which will be next? 2 and 4. And what would be true about 5?
It would be 0 because that's not.
Exactly. Sure, 5's got an R that is ever increasing. But that R and that V are not perpendicular. So we would say it has no angular momentum there. Okay, which particles have a negative angular momentum? Meaning, do your right-hand rule. So you point your right hand towards the R, curl your fingers towards the V. Which one's going to be up, which one's going to be down?
I think 1 and 2 have to be down.
1 and 2? Just one of them.
Going in the opposite direction. Has 3 and 4?
Well, but it's about point O. All right. Okay, so 1, right hand in the direction of R, cross towards the V. That's going to be a positive angular momentum. So that's up. Okay, but down here, R. Oh, I gotta break my right hand to do this one. Okay, point towards R is down. Cross towards V this way. That would be down.
Okay.
So 2 is negative. Which other one is negative? 3 or 4? We said 5 is 0.
3.
Good. 3, okay, so R is this way, cross towards the V. That would be negative. Okay. All right, net, of course, add up if needed. You don't have that written? And again, that M times R cross V, that's for a point mass. Which we will treat these two things as point masses. So this says a light rigid rod, because we do actually have a moment of inertia formula for a rod, but when they say it's light and they don't tell you the mass, ignore it. But a meter in length joins 2 particles with masses 4 and 3 kilograms at its ends. The combination rotates in the xy plane about a pivot through the center of the rod. Determine the angular momentum of the system about the origin when the speed of each particle is 5 meters per second. So, pretty straightforward. Okay, so for this one, M, R cross V. So what's M? Three. What's the radius to the rotation point? Yeah, the whole thing's meters, so 0.5. And then it's velocity, 5. Is that perpendicular to the radius?
The way it's going.
Yeah, so from what they've told us, yeah. Otherwise it'd be breaking apart, I guess. But so that's a tangential velocity. Okay, so what is that? 2.5 times 3. What is our unit, actually, even looking at the formula? A little more.
Kilogram, meters.
Yeah, meters second, meters squared per second. Okay, and here, just same thing, 4 times 0.5 times 5. Wait, 10? 9? Let's go with 10. All right, now before we add them up, although since they're attached, this should make sense, we just got to check the direction. They go in the same way. Would our right-hand rule give us the same angular momentum? R cross V, okay, that's up. R cross V, of course, that's up as well. So same direction, so now we just add them up. Okay, also true. When we were studying linear motion, the derivative of momentum was force. So the derivative of angular momentum is torque. Or you think of change in angular momentum over time. So 279 kind of relates to that real quick. All right, Zach, 3 for 3.
All right, we got it. Wes.
Oh, your first strikeout. Brandon. Wes was next, though.
You have to tell, you looked at me.
Yeah. Oh, darn it. Well, maybe he was pure the first 2 times. All right, so Brandon, page 279, number 5.
I was on my chair.
Yeah. The figure shows the position vector r of a particle at a certain instant and 4 choices for the direction of force that is to accelerate the particle. All 4 choices are in the xy plane. Rank the choices according to the magnitude of the time rate of change they produce in angular momentum, which is essentially saying, it's saying rank them by the time rate of change of angular momentum, rank them according to torque. So looking at your picture, which force would provide the greatest torque? F3, because it's perpendicular. Good. Next one. Okay. And what's true about F2 and F4? They would be 0 because they are not perpendicular to R. Which one would result in a negative rate of change? Really just a negative direction from our right-hand rule. F3. R. F3 is that way. Be down. Very good. All right, I think we have one more like that, maybe.
We need to.
Okay. How am I doing? How many more slides? 4. Okay. Okay. So you can follow along the little substitutions here, but we can also, of course, have angular momentum for a rigid body, not just the point masses. This was our formula for a point mass. And you already told me that one, where we think of regular momentum as mass times velocity. That would be I omega for rotational. (282), checkpoint number 6. Okay, in the figure, a disk, a hoop, and a solid sphere are made to spin about a fixed central axis, like a top, by means of by strings wrapped around them, with the strings producing the same constant tangential force on all 3 objects. The 3 objects have the same mass and radius, and they are initially stationary. First, it says rank the objects according to their angular momentum about their central axes. And let me back up to that other formula for a second. Yes. They should be the same. If they have the same radius and the same force, then the torque should be the same. So their angular momentum should be the same. Very good. Okay, and then it says rank them according to their angular speed, greatest first, which is where we want this formula. We said they all have the same angular momentum. So the biggest angular speed is going to have the what I? Smallest I. Actually, it's a sphere first. Wait, sphere, then what? Then disk, then hoop. Very good. Hoop should be clearly last because it's got, its mass is the farthest away, so it should have the greatest I. All right, good. Okay, we just have more of our relationships. Almost. 2 more slides?
Yeah, this one and the next one.
2 more slides. Okay, so of course we had conservation momentum before. That's what we did our air track lab on. That's what you're doing your video labs on Sunday night. But we also have conservation of angular momentum, which is what Connor will demonstrate for us. And the most common explanation of this is the ice skater, the figure skater. Because you got to think about something that can change its I, but figure skater is rotating in a circle, and let's say she has her arms spread. Is she going to have a bigger I with her arms spread or smaller? Bigger, more mass farther away. If she brings her arms in, she's still the same mass, of course, but she is changing her moment of inertia, so that will go down. And what happens to her speed when she brings her arms in? She speeds up. She always goes faster in a circle when her arms are tucked. Ta-da. Okay. 284. Oh, I should just let you quit while you were ahead. It's Connor.
Again.
You didn't go today.
No, but I went last time.
I shuffle them. Okay, and this is actually kind of like your web quest. Or maybe you've already done it with the beetle. All right, checkpoint number 7, Connor says, a rhinoceros beetle rides the rim of a small disc that rotates like a merry-go-round. If the beetle crawls toward the center of the disc, do the following: increase, decrease, or remain the same. A, the rotational inertia, meaning I. Correct. If the mass more moves towards the center, it would decrease. What about the angular momentum? Good. It should be conserved. The whole thing is conserved. And then what about the angular speed? It would speed up, like the ice skater pulling her arms in. Okay, so quick problem here. And then we'll demo our ice skater and other fun things.
Is Connor going to be an ice skater?
Yes, but not on the ice.
Is he going to?
We can only hope not. Well, your call. Okay, so here we have these 2 objects rotating. A cylinder with a moment of inertia I1 rotates about a vertical frictionless axle with angular velocity omega I. A second cylinder that has a moment of inertia I2 and initially is not rotating drops onto the first cylinder. Because of friction, the 2 move as the same omega F. So this just drops, sticks, calculate omega F. And just as a guess, is omega F going to be bigger or smaller than omega I?
Bigger.
And of course, they even drew it for you. It's gaining I. It's gaining more moment of inertia. So omega F should go down. So this is just conservation of angular momentum with the pen. They're not point masses, so we're not going to use the m r cross v. But Li is, just I1 omega I. And LF, how would we have to write that? Almost the same. Exactly. So if you want to solve for omega F, just divide by this. Ta-da. Okay. Put your arms out. Don't break my stuff. Wait. Are you going to hit my board? Let's scoot you just up a little bit.
What's going to suck is if you're going fast and you drop it.
Okay. If you got to bail out, don't hit my laptop. All right, so arms out. So we're not changing his mass. We are adding a little weight to his arms to make this a little more dramatic. We're going to spin him, and then when you feel comfortable, bring your arms in, as the ice skater would. Another option for slowing down other than stepping off the platform would have been what? Spread them back out. Okay. Trial 2, put those down.
That's actually a lot of fun.
Okay, get on the platform. Hold like top and bottom. We're going to get this going. Let's say we'll get it going this way. What is the direction of angular momentum of the tire if it's moving like this?
Up.
Up. Okay, so that wants to be conserved. Up should be conserved. But we're going to have Connor flip it over, which would then make the direction down, which is a problem. How can we conserve up if he just flips it over? Oh, not as dramatic. Let's bring you back to the center, if you can. Okay. I'll go this way. Now this way. Okay. Too much friction. But what does happen to Connor when he flips it over? He turns. Because we're trying to keep that angular momentum of up. So if you look at Connor's feet, he's kind of going like this with an angular momentum of up. If you step off of it, the platform, and just hold it like vertical. Okay. This is just plain hard to do. Because just now move the wheel all around. Can you feel it pulling on you?
Yeah.
It's trying to like flip his body like feet overhead. If you can imagine him being in space to conserve momentum, he would be flipping all over the place. Of course, we have external forces preventing that, but.
You have to do that. I want to do it.
Would anybody else like to try? If you can get this going a little faster, that's a little more dramatic, but. All right, spin Zach.
Step it up and I can go